to switch to introduce the next speaker, and the next speaker is Giulia Fischetti. And the title of the talk is Ensemble Reconstruction of the Worldwide Airport Network. Giulia is finishing now her PhD studies, and she is now actually in Zurich, I think. So please, Giulia, you can start.
Okay, thank you for the kind introduction. Let me share my screen. Okay, so hello everybody. I would like to start by thanking the organizers for inviting me here to talk about my work. So today I want to show you how to build a model able to reproduce the properties specific to the worldwide airport transportation network, and how this model can then be used to for forecasting epidemics dynamic on the network. But before diving into this topic, let's talk about the concept of network in general as a tool, and a very effective tool to display and study interaction among individual elements in a system composed of many elements. And networks, as a matter of fact, have been used to describe very different systems, from scientific collaboration. Here I'm showing, for example, the Nature Citation Network, or financial relationship among banks, or the neural connection within the brain in the brain networks and connectome, or even the contagion contacts between infected and susceptible individuals in epidemic networks. And the very interesting thing is that all these systems, which belong to different fields and different to very different fields, they all share similar properties. So one thing is that from like very simple interaction, one can retrieve like complex behavior. Then also the fact that usually the number of connections among the individual parts are scale-free, like they follow like a scale-free distribution. And also, like usually these networks have a high level of clustering, so there is like high interconnectivity among the single parts, and this is also described as a small world. So like the path, the smallest path, like between two elements or two nodes on the network is quite short. From the mathematical perspective, the definition of graph is quite simple. So a graph is a set of nodes connected by edges, and the interaction among the nodes is encoded into a binary adjacency matrix, where the non-null entries are the one where actually there is a connection between the nodes. And an important quantity that describes the network is the number of connections for each node. There is the degree, and if the edges can be either undirected, but also they can have a direction. And in this case, it's interesting to introduce and to define the incoming and outgoing connection of one node as the in degree and the out degree. Furthermore, the connection could all be the same, or they could be differentiated by some quantitative weight. So the network is said to be weighted. And in this case, we will define the sum of the weights pertaining to one node as the strength, or the in strength and out strength in the directed case. We could also do like statistical physics on network. So like in a very like straightforward way, or like very similar way to traditional statistical physics, we can define an ensemble of graph where each graph in the ensemble is associated with a certain probability. And of course, such probability is normalized to 1. And then the probability of each graph in the ensemble can be determined through the maximum entropy principle. So maximizing the Shannon entropy of the ensemble. And in this case, maximizing the Shannon entropy, considering soft constraints, and of course the normalization of the probability, we will get the so-called canonical ensemble of network, which will give this functional form for the probability, which is an exponential. And so that's why also we call this kind of theory like exponential random graphs. And then like this definition still depends on the Lagrange multipliers, which can be retrieved if we fit the model to the observation of a specific graph that for which we want to reconstruct the topology. And this is done like maximizing the likelihood function. Doing like or following this procedure, we can, for example, constrain the degree sequence, and then we will obtain the binary configuration model. And this will give like sparse reconstruction of the network, which is a welcome feature, but it's just a binary model, so we will not have a weighted network. So if we have if we want to reconstruct the topology and like the properties of a weighted network, we should also, for example, constrain the strength sequence. And in this case, we will have the so-called weighted configuration model. And however, in this case, we will have a weighted network in the end, but the reconstruction is very dense. In some cases, is like completely fully connected network. But like in reality, we don't have like, it's not so common to have fully connected networks. So we would like to have like a sparse reconstruction, but with weights. And this can be achieved by constraining both the degree and the strength sequences within the enhanced configurational model. Now, coming back to the topic of the talk, the worldwide air transportation network. Here I'm showing you a snapshot of the worldwide air transportation network in January 2019, and like bigger palettes represent airports with larger or like with larger number of connection. And now the question that we wanted to ask is like, can we build like a statistical physics model for the worldwide air transportation network? And this is already interesting per se, because of course we will have insight on how this transportation system works, but also we are interested in having like a model able to provide an accurate forecast of epidemic dynamics. And so the data set that we had consisted in user basins. So the nodes in our network are not the individual airports, but for example, here I'm showing that for the case of the city of Rome, we have two main commercial airports, which are Fiumicino and Ciampino. And in this case, their data is averaged and like aggregated under the basin of Rome. And those basins are defined by geographic coordinates and complemented with the population size. So the network is weighted and undirected, and of course the weights on the network are the average flows of passenger between two basins, and the degree are just the ingoing and the outgoing flight connection per basin, and the strength are the basin's passenger capacity. The datasets with that we work with had these features. So we found, as also other airport network datasets have displayed, scale-free degree distribution and strength distribution. We also found a superlinear relation between the degree and the strength. And also we investigated the role of geographical distance in the network, and so we saw that the edge probability experimentally decays exponentially as a function of the distance. And also, if we divide the user basin within some geographical regions, we see that there is a modularity in a modularity of 0.64 for the real airport network. So the goal is to build a model of the one which is both sparse and weighted, and with these features that we have here. And indeed, the topological features of the airport network are really important if we consider the airport network for forecasting epidemics. And this, for example, was already highlighted in this work, the early 2000s, where the pattern of the epidemics measured by the entropy of the infected individuals across the network has been compared for the real network and two null models. One is just a random graph with the same densities as in the real density of connection as in the real network, and also another null model which is obtained by keeping the same topology of the real network, but having like uniform fluxes which are equal to the averages of the real network. And as you may see, like when the topology is preserved, the pattern of the epidemics is more similar to the real one. However, such like the topological data, the real topological data are not always available. So we really need like a model to provide a substitute for them. And some previous models that have been considered for it, of course, take into account the distribution of the degree as a scale free, so as a power law, or the spatial dependence on the probability, on the linking probability, introducing, for example, this term which is fitted on the real probability of having a link at a certain distance. And also the weights usually are retrieved with like a gravity model, sometimes introducing also the superlinear relation between strength and degrees. What we did, or like a good candidate for the reconstruction of the model of the airport network could be the enhanced configurational model. However, considering that we have like more than 3,000 user bases in the network, we would need to solve like very large equation system. So we did a workaround. We consider the fitness ansatz, and in a two-step procedure, we firstly recovered the binary topology of the network without directly retrieving the Lagrange multiplier by constraining the degrees and the strengths, but just considering that the degrees of the network are somehow directly proportional to, or are like proportional to the strengths, and then we fit the parameter z to match the total number of edges in the network. And then once the binary topology is retrieved with a gravity corrected or density corrected gravity model, we assign the weights to the links. Here this W represents the total weight of the network, And this prescription allows to retrieve on average the values of the strengths of the nodes. With this prescription, we find that the degree sequence and the weight sequence are especially retrieved quite correctly. There is a bit of, in this case, for example, the lower degrees are a bit underestimated and the larger degrees are overestimated, but overall, there is somehow good agreement. And also for the experimental linking probability, if we look at it compared to the model linking probability, we see that there is some discrepancy, but somehow it follows somehow like the identity line. Looking at other network properties, we see that the model can interpolate the degree versus strength dependence. However, the dispersion is not the experimental dispersion is not reproduced, and also there is a poor reconstruction of the distance dependence of the edge probability as a function of distance, and also no modularity. So in order especially to enforce these properties, we introduced a new model which consider the user basin divided into 11 geographical regions. And so in this case, we are considering the strength of a node or of a basin E with the geographical region of node J. So with we are summing over all the connection with all the basins which are part of the geographical regions of which the J basin is part. So we in this way we enforce the community or the community structure, and also we enforce the superlinear relation between degrees and strength by including an exponent on the strengths, and also we include a spatial dependence, which is modeled on the true edge probability as a function of distance. And again, to retrieve the binary topology, we fit on the number of edges between two geographical regions. And after the binary topology is retrieved, we assign the weights always with the density corrected gravity model. And in this case, this prescription preserved the average of the strengths per geographical region. We see that the prediction of the degrees and of the weight sequence is improved. The prediction on the experimental linking probability, and not especially, but what is really interesting is how the model is able to reproduce the relationship between degrees and strength with the full dispersion captured, and also how is able to reproduce the dependence of the edge probability as a function of distance. Of course, also the modularity is reproduced, but I mean that was expected since we reinforced it in the model.
Giulia, your time is going also to finish. Yeah.
Okay, so I will speed up. So what we did, since we wanted to also forecast epidemics spreading on the network, we perform meta-population SIR models on both the real network and on the reconstructed network. This means that in each node we have a population which is divided into susceptible, infected, and recovered individuals. And these are the equations that constrain or that rule the dynamics of the epidemics within each node. And then, of course, the population is allowed also to travel with some mobility that is modeled on the weight metrics of the network. What we find out here, I'm showing the model that we consider. Model K is the simple fitness ansatz, and model C is the model with the modularity and with the geographical regions enforced, and R is just like a null model, like a random model, just as a benchmark. And as you can see, if we look at the percentage of each population as a function of time, the most promising model seems the model with the structure. This can also be seen like a bit pictorially on this map, where the kind of more orange value represent like lower infected individuals, while the more purple, more black represents like more infected people in the node. And as you can see, if we set like one time in the simulation, so like a screenshot, the model seed can capture this specific heterogeneity that we have in the real network, while the other two models, the fitness model and the random model, are more homogeneous. And this is also, I mean, this is also captured quantitatively if we consider like somehow the spatial error. There is the root mean square error on the prevalence, which is like just the infected number of infected individuals in the node, or if, for example, we consider the distribution of infected and then we compute the entropy of such distribution, we can compute the temporal error, so the root mean square error. And as you may see, again the model C, which is the one with the structure, is the best performing. So in the end, I think I've tried to convince you that if we enforce especially the degree heterogeneity, the spatial dependence, and the community structure, we have very effective reconstruction of the airport network that can be used to reproduce contagion dynamics. So far, we used like approximation of models that are approximations, and then maybe a next step would be to go to more rigorous model derivation, and also next step would be to test on more realistic contagion dynamics. I want to thank my supervisors and collaborators, and thank you all for your attention.
Okay, thank you very much, Giulia. And one question, yeah. Please, if there are. I don't see question, even if the seminar has been stimulating and interesting. So I want to conclude thanking all the speakers of today, the two speakers, and Mattia and Giulia. And if there are questions, we can write to them. Maybe they will answer. And the next seminar are on 13 November. And we will receive an email about that, and maybe we can conclude with this. Okay? So thank you, Alberto Bassanoni, for having organized everything, and I think we can stop here. Okay? Thank you again, Giulia and Mattia. Bye-bye.
Thank you all. Thank you.
Bye.
Bye.
Thank you.
Bye-bye.
Bye-bye.
Ciao a tutti.
Ciao, ciao a tutti. Ciao.
Ciao.